In lesson 6.7, we'll be working with polynomial equations. We mainly are going to solve them, but we are going to learn some other properties about the roots that we have with polynomial equations. And right off the bat, we start with this very important theorem called the fundamental theorem of algebra. That says every polynomial equation of degree n has at least one complex root, and the corollary, or another theorem that's easily proved from this theorem, states that every polynomial equation of degree n, so degree n has exactly n complex roots, including multiple roots. So this is saying whatever our degree is, that's how many complex roots we'll have. And notice we're talking about complex numbers, so this could include imaginary numbers. And this includes multiple roots, and this means the same number, like 7, could be a root more than one time. So we don't just count that 7 once, we would count it all the times that it would be a root. So let's just jump right into these examples here. This first one says, state the number of complex roots and solve the polynomial equations. So as we look at this first one, we notice the degree of this is 3, which means that's how many complex roots there will be. So there'll be 3 complex roots. And then for factoring them, or for solving those equations, what we can do, we can either use what we learned with the rational root theorem and try to factor this using synthetic division, or what we can do is we also learned factoring by grouping, and we know that if we have a cubic function, that's one of the options that we could use. And looking at this one, I think this will be a good candidate for this. So I'm going to rewrite this. I'm going to go ahead and group the first 2 terms and group the second 2 terms. And over here, we have an x squared in common. What's left over is a 3x minus 1. And then here we can factor out a 9. And we have 3x minus 1. And remember, with factoring by grouping, what we do now is we look and we notice we have a 3x minus 1 in common, so that can be factored out. And what's left over? Well, this x squared plus 9 is left over. This is still equal to 0. And we remember, if we have things that multiply to equal 0, we can set them equal to 0. Now this one is close to being something that's familiar, but it is not. So here we can have 3x minus 1 equals 0. And x squared plus 9 equals 0. Add 1, divide by 3. So x equals 1/3. That's one solution. Over here we can subtract 9. Take the square root. When we take the square root of negative 9, we get square root of negative 9. We know we can't take the square root of a negative, so we know we have an I, and I should have put plus or minus here. X equals plus or minus the square root of 9 is 3, and we have I. So our solutions are x equals 1/3 and x equals plus or minus 3i. So we had 3 complex roots, and we found all 3 of those. So if we put 1/3 back in here and solved it, it would make it true, or if we put either of these 2 back in here and simplified it, it would make it true. Coming over this next one, we have x cubed equals 5x minus 2. What we want to do is we want to get everything to one side. Well, first of all, we want to know the number of complex roots, and that's also 3, so we still have 3 complex roots. And then what we can do is we can solve this, and once I said it earlier, we want to get everything to one side. Subtract 5x and add 2 to both sides is equal to 0. Here we cannot do factoring by grouping. So what we'll do is we have C. Our possibilities for C are plus or minus 1 and plus or minus 2. Our possibilities for D, which is the leading coefficient, is just plus or minus 1. Well, that's pretty easy. C over D then would be 1 over 1 and 2 over 1, so still just actually the same as C. So plus or minus 1, plus or minus 2, and so what we can do is we can use synthetic division and start trying these. So we have 1, x cubed, we have 0x squared, so we're going to put a 0 in here. Negative 5 and 2. Let's try using 1, so we bring down our 1. I forgot I didn't show this shortcut method yet, but we bring down our 1, and then we do this. Still, we multiply, add. 1 times 1 is 1, plus 0 is 1. 1 times 1 is 1, plus negative 5 is negative 4. 1 times negative 4 is negative 4, plus 2 is negative 2. So that one does not work. Remember, we want to get a 0. Let's try negative 1. Again, we bring down our 1. Make sure when we do it this shortcut way that we're always looking back to our original equation. So negative 1 times 1 is negative 1, plus 0 is negative 1. Negative 1 times negative 1 is 1. So 1 plus negative 5 is negative 4. This would be positive 4, and this would give us a 6. All right, well, those two didn't work. Let's try 2. Bring down a 1. 2 times 1 is 2, plus 0 is 2. 4, or 2 times 2 is 4, plus negative 5 is negative 1. And 2 times negative 1 is negative 2, plus 2 is 0. And so 2 works, which means we're going to have to really squeeze this in here. X minus 2 is a factor. Our polynomial that's left over is x squared plus 2x minus 1. And this doesn't factor, but we could use the quadratic formula to solve this. End up with x equals negative 1 plus or minus root 2. And so we have our 3 answers. So there's 2 of our answers, and then our other answer was 2. So here are the 3 complex zeros for this equation that we solved. The next one is actually x to the 4th power. We know that there's going to be 4 complex roots. We can't factor by grouping, so we'll use synthetic division and the rational root theorem to help us. So possibilities for C, possibilities for D, and so C over D All right, now what we can do is we can try these. Let's go ahead and try 1. Bring down the 4. 4 times 4, 16, that's negative 12. 1 times negative 12 is negative 12, plus 15 is 3. 3 plus 4 is 7, and 1 times 7 plus 4, negative 4 is 3. Let's try 2. Bring down the 4. That's 8. 8 and negative 16 is negative 8. 2 times negative 8 is negative 16 plus 15 is negative 1. 2 times negative 1 is negative 2 plus 4 is 2, and 2 times 2 minus 4 is 0. So this works. So x minus 2 is one of our factors. and we're left with this polynomial. Now, what I want to teach you here, so we're going from an x to the fourth down to an x cubed minus x plus 2. So don't keep going with this polynomial now. Now come to this cubic polynomial. So we have this cubic polynomial. We could keep using synthetic division, and what you would do is you would start over again. So you would take your coefficients, 4, -8, -1, and 2. And something else I want you to realize here is we can redo our rational roots. And also, since 1 did not work for this one, it will not work up here. So we can keep trying. We could try 2 again. So 1 didn't work, so it won't work. 2 did work. It could actually work again, but it might not. So it doesn't hurt to try. And I'm going to try it, but then I want to show you something else. Bring down the 4. 2 times 4 is 8, that makes 0. 2 times 0 plus -1 is -1. 2 times -1 is -2 plus 2 is 0. So it actually worked again. We still have this x minus 2 from down here. We have another x minus 2 because 2 worked again. And then we have what's left over here. And so we factored this, and now we can solve. Now these are the same, so we only have to solve those once. So we know x equals 2. And what we do here, since it worked twice, what I do is I'll put multiplicity, actually I abbreviate, multiplicity 2. And then we want to solve this one. Well, this is 4x squared minus 1 equals 0. We can add 1 to both sides. Divide by 4. Take the square root, make sure we put plus or minus. So plus or minus, square root of 1/4 is the square root of 1 over square root of 4, which is 1/2. So our answer here is x equals 2, multiplicity 2, and then plus or minus 1/2. And so I know it looks like we have 3 answers. We have a 2, and then a 1/2 and a -1/2, but we have 4 because this 2 is worked as a root twice.